In the colossal collision of a mega-galaxy cluster, dark matter surpasses normal matter in its advancement. Greetings, everyone. Today, we will be delving into the fascinating subject of dark matter outpacing normal matter in a galaxy cluster collision, primarily due to its limited interaction with electromagnetism. Through the utilization of multiple telescopes, researchers meticulously examined the MACS J0018 5-cluster collision, meticulously mapping the velocity of both dark matter and normal matter. Remarkably, the unique alignment of this collision allowed for an unprecedented observation: the separation of dark matter from normal matter. This groundbreaking discovery not only provides valuable insights into the behavior of dark matter, but also paves the way for future investigations aimed at unraveling its enigmatic nature. Without any further delay, let us embark on our enlightening discussion. Gravity is the force responsible for binding together galaxy clusters, which are immense structures in the cosmos. Interestingly, a mere 15% of the mass contained within these clusters consists of ordinary matter, encompassing the materials that give rise to planets, humans, and other observable entities. The majority of this ordinary matter takes the form of heated gas, while stars and planets constitute the remaining portion. The overwhelming 85% of the cluster's mass, on the other hand, is composed of enigmatic dark matter. During the collision of the clusters known as MACS J0018, 5 plus 1626, the galaxies themselves remained mostly unscathed as a result of the significant distances between them. However, the immense gas reserves located between the galaxies experienced a collision, leading to turbulence and intense heating. While gravity affects all forms of matter, normal matter also undergoes electromagnetic interactions, causing it to decelerate upon collision. In contrast, the dark matter within each cluster remained unaffected and passed through the collision without any disturbance. Drawing a parallel to a colossal collision involving numerous dump trucks transporting sand, Emily Sillich, the primary author of a recent study published in the Astrophysical Journal, likens the situation to the behavior of dark matter. Sillich, a graduate student collaborating with research professor Jack Sayers at Caltech, underscores this analogy. Data collected from multiple observatories, such as Caltech's Sub-Millimeter Observatory, relocated from Mauna Kea, Hawaii to Chile, the W.M. Keck Observatory, NASA's Chandra X-ray Observatory, NASA's Hubble Space Telescope, the European Space Agency's retired Herschel and Planck observatories, and the Atacama Sub-Millimeter Telescope experiment in Chile, has led to this remarkable discovery. While certain observations span several decades, thorough analysis has taken place in more recent years. The Bullet cluster also exhibited a distinct division between dark matter and normal matter. When the clusters collided, the dark matter appeared to be ahead of the visible hot gas. In MACS J0018, 5 plus 1626, a similar phenomenon occurred but with a different alignment. One cluster was approaching Earth directly, while the other was moving in the opposite direction. This particular orientation provided researchers with the opportunity to map the velocities of both types of matter, revealing their distinct separation during the collision. According to Jack Sayers, the Bullet cluster can be likened to observing a car race from a spectator's perspective, where one captures intermittent images of cars moving horizontally. However, in our scenario, it is comparable to standing with a radar gun and gauging the velocity of a car as it approaches us head-on. Using CSO data, Sayers and his team initially detected the kinetic Sunyaev-Zeldovich (SZ) effect in 2013 while studying the galaxy cluster MACS J0717. This effect is measured to determine the speed of gas clouds in galaxy clusters by observing the change in brightness caused by photons from the cosmic microwave background scattering off electrons in hot gas and shifting due to the motion of the gas clouds. When we initially employed a novel camera at CSO to study galaxy clusters in 2006, the Sunyaev-Zeldovich effect served as a fresh observational tool, explains Sunil Golwala, the PhD advisor of Sillich. With the advent of next-generation instruments at CSO's new site in Chile, we expect to encounter even more unexpected discoveries. Using the kinetic SZ effect and data from the Keck Observatory, Researchers were able to measure the velocities of gas in various clusters and indirectly infer the speed of dark matter by 2019. While their understanding of cluster orientations was initially limited, they observed something peculiar in max J0018-5. The hot gas exhibited movement that was contrary to the direction of the dark matter. When we stumbled upon velocities moving in contradictory directions, our initial assumption was that there must have been an error in the data. This confusion was shared by our simulation colleagues, who were equally perplexed. However, everything became clear when Emily joined our team and shed light on the situation. Silic utilized data from the Chandra X-ray Observatory for her doctoral dissertation, employing it to create visual representations of gas temperature, distribution, and the intensity of shock waves within clusters. Silic emphasizes the immense energy released during cluster collisions, comparing them to the magnitude of the Big Bang. By analyzing gas temperatures, Chandra provides valuable insights into the age of the merger and the recentness of the collision. Collaborating with Adi Zitrin from Ben-Gurion University, the team incorporated data from the Hubble telescope to map the distribution of dark matter through gravitational lensing. Assisting in the simulation of the cluster collision was John Zhu Hone, a member of the Harvard and Smithsonian Center for Astrophysics. By merging these simulations with data gathered from telescopes, the team was able to determine the collision's shape and progression. It was revealed that prior to the collision, the clusters were approaching each other at a speed of approximately 3,000 kilometers per second, which amounts to roughly 1% of the speed of light. This comprehensive comprehension clarified the perplexing phenomenon of the dark and normal matter moving in seemingly opposite directions. The researchers have set their sights on conducting additional studies in order to unravel the enigmatic nature of dark matter in the future. Silic emphasizes that this study serves as a stepping stone towards more comprehensive investigations into the intricacies of dark matter. With the unveiling of a direct probe, we are now able to observe and understand the unique characteristics and behaviors exhibited by dark matter. After devoting close to 20 years to unraveling this intricate puzzle, Sayers reflects, "Our efforts have finally paid off, and we have gained a comprehensive understanding. Our hope is that this breakthrough will pave the way for fresh opportunities to delve into the study of dark matter within clusters." Funding for the research project known as ICM Shocks. Paper 1. Methodology overview and discovery of a gas dark matter velocity decoupling in the max J0018-5 plus 1626 merger was provided by various organizations, including the National Science Foundation, the Wallace L.W. Sargent Graduate Fellowship at Caltech, the Chandra X-ray Center, the United States-Israel Binational Science Foundation, Israel's Ministry of Science and Technology, the ATLAST Project, and the Consejo Nacional de Humanidades, Ciencias y Tecnologías. To support our channel's growth and ensure broader awareness, kindly hit the like, share, and subscribe buttons. This will help us reach more individuals and disseminate valuable information. Thank you in advance.